All right, so this week we're going to talk about chapter F3.1, which is advanced pixel-based image transformations. As before, we've broken this down into three main pieces. We'll do a quick chapter overview, then dive into the theory and the practicum. If you're interested in following along, excuse me, with the slides, here's the link. And then Jeff, maybe if you wanted to drop that into the chat, that would be fantastic. So just a quick overview. This chapter really aims to introduce some of the more complex pixel-based image manipulation approaches. And in order to accomplish this, we're going to first try to understand what linear transformations are and why pixel-based image transformations are useful. We'll then learn how to use expressions for band manipulation. I believe last week, we saw a preview of this, and we'll also introduce you to some of the most common types of linear transformations. This includes PCA and the HSV transformation, which is used for pan sharpening. And then in order to do this, we'll be using arrays and functions in Earth Engine to apply these linear transformations. So this chapter assumes that you know how to do everything in F1 and F2, as well as using the drawing tools to create points, lines, and polygons, which is chapter F2.1. I won't actually go over that because it's been covered previously. Importantly, this chapter also assumes that you have an understanding of the basic operations of matrices. This includes matrix multiplication, and transposing matrices. I think those are the two major ones we use. Ideally, you'll also understand eigenvectors and eigenvalues, but you can kind of get away with not 100% understanding that. The idea of orthogonality is also important, which is basically just things that are orthogonal in space. What's the word I'm looking for? Perpendicular, but applied to multi-space, multi-dimensional space. If any of these concepts you're not familiar with, please feel free to listen in. And then I highly recommend after this presentation, you go Google something like Introduction to Linear Algebra, or basics of matrix multiplication. There are so many fantastic resources on the web that will pretty easily teach you these things. There's also a number of YouTube channels that are kind of dedicated to these things, including in both the data science realm as well as the map analysis realm. So lots of good resources out there. I won't be getting into it too much other than to explain those concepts a little bit in the Earth Engine application. So why do we want to use these advanced image transformations that aren't just, addition and subtraction of the different bands as we saw, a month ago now in chapter, I think it was 2.1. Jeff, correct me if I'm wrong. The real answer is that they can be better at detecting subtle changes. And this is largely because they can take lots of different information and kind of smush all that information and kind of mathematically extract some of the most important pieces. So one of the approaches that we'll be talking about today is PCA, and some of you, which is principal component analysis. And some of you may be familiar with this from using it in other contexts. And just like those other contexts, here it can really be used to kind of extract some of the pieces of the image, some of those signals from the Earth's surface that really distinguish different land uses. So there's two main types of these advanced image transformations. The first is pixel-based approaches, which use linear transformations and matrix algebra. That's what we'll be talking about this week. And then next week, we'll be talking about neighborhood-based approaches. So these are things like zonal calculations. what we'll cover this week and next week are really important tools for future chapters, including F5 through F9, or sorry, F4.5 through F4.9, as well as many, perhaps most, of the applications chapter. So this is a really important piece to get to know. It's also frequently used in the scientific literature. So if you are, if you're involved in publications, or if you're reading the scientific literature in order to teach yourself more about methods, these are all very commonly used, usually in conjunction with other methods. So 2 quick things before we dive into the practicum. First, in order to access the book scripts, there's a link in the book that you click. If you don't see it appear right away, please hit the refresh button and it will pop up. And 2, if you need more help for some of the functions, and I think these are good practices, even if you understand them, because frequently you can learn more efficient or more interesting ways to apply the functions. There's the Docs tab, which is here on your main Earth Engine screen. There's also a question mark that will take you to the user guides. The GEE has extensive user guides. And then there's always things like Stack Exchange that are extremely valuable resources. All right, so let's dive into section 1, which is manipulating images with expressions. So we previewed expressions last week to create a map for our linear regression. I really like expressions. They are a tidy alternative to doing manual calculation, such as what we did. It's F2.0, put it in there for myself, with NDVI. Hold on 2 seconds, I'm getting a ding. Okay, great. The expressions have 2 key parts. The first is to define the equation, and the second is to define the variables. It's called a map. So for expressions, for the expression arguments, there are a number of different things that you can use. You can use your arithmetic operators, so plus, minus, etc. You can use relational operators, logical operators. This is your and, or. Ternary operators, so if true, if false, and some, but not all, of the JavaScript math functions that are included in Google Earth Engine. So if you're getting deep into these, you may need to check which of the JavaScript math functions are available versus not, but most things can be handled with these first 4. So it's usually not too big of a deal. For the map argument, this is technically optional, but I highly, highly recommend it because it really helps with the human readability of code. So this is really important if you're sharing code with collaborators, or if you're sharing code with your future self in 6 months. You will thank yourself for naming things logical things instead of just, band names or, combinations of letters and numbers that don't actually say what they mean. So just to quickly chat about this, I pulled an example of an expression here that we'll go ahead and calculate. And you can see that here's the variable definition, image, calling an expression on the image, and then the 2 pieces, right? Here's our expression piece, and here's our map piece. So like we just talked about. So this expression, involves some constants, but it also involves 3 bands, which we've gone ahead and named human readable things, which are near infrared, red, and blue. So anytime we see this, it doesn't matter if it's tomorrow or 6 months from now, we'll be able to be like, oh, right, it's, these band names. And we don't have to remember that band 8 is our near infrared, right? So it's just called near infrared. So that's kind of a quick setup of how that works. Now let's go. Let's see. Just gonna pull code window over. And we actually have two examples of this implemented, which is our checkpoints A and B. They're in different locations using different indices. And so we're just going to talk about one of them today because they're basically the same. The first is an implementation of EVI using Sentinel-2. And in this checkpoint, what we do is we first calculate it manually, and then we calculate it using the expression so that you can kind of learn how the expression is a replacement for doing all those kind of, I'll call them manual calculations. So in the code, the first bit is to import and filter the imagery. And then I will point out all of this is the manual calculations, right? So first selecting the images, then we subtract and multiply, then we do some more multiplications for the denominator, and then we divide the numerator by the denominator, and then, rename it. So that's what we see here. I'm just going to zoom in. I'll zoom into the airport pretty far so that you can see kind of what that looks like. So red is water, white is impervious surface, human surfaces, and then the green is the vegetation. Now, in contrast, so that's mapped here. In contrast, this expression here replaces all of this, and it's significantly more readable because you can see it's written out the way you would handwrite an equation instead of multiple different steps to calculate the numerator and then the denominator, etc. So I find this hugely more useful and hugely more easy to understand and read. So here's that expression with the expression piece and the map piece. And then we just map that. And you can see if we go ahead and turn on that EVI expression, then nothing changes, which means they're both calculating the exact same values. And of course, as always, you can use the inspector, and you can see that, again, they're calculating the same value. So if you want to, I'm just going to load it here real quick. The F3.1B checkpoint does the exact same thing for calculating BAI. So this is a fun one because it's for burn detection. And it's really fun and dramatic because in the satellite imagery, it's really hard to see. You can kind of tell that it's darker than the surrounding landscape, but then you use that BAI indicator and all of a sudden all this red is burned and it just lights up. So, but it's just another example of using an expression. Okay, so section 2 is manipulating images with matrix algebra. And this is where we start getting into the matrix algebra, linear algebra pieces that I was talking about before. And again, if any of these concepts aren't ringing a bell for you, I highly recommend using this section to kind of pull out the keywords and then Googling things like introduction to or basics of blank in order to get some more information. So Google Earth Image does matrix algebra using something called arrays. And we will be specifying arrays, creating additional dimensions, reducing dimensions for this section. And we'll be doing 2 examples in order to learn those functions, tasseled cap and PCA. So what are arrays? It's a very complex question. And I will say, this is something, it doesn't sound hard, but the way that it's implemented in Google Earth Engine definitely trips up people kind of a lot. And I know it was a little bit difficult for me to understand kind of at first. And I will say a large part of that is because I come from an R programming background. And so I'm used to a matrix just being a matrix, right? So thinking of matrices as lists of lists took me a second. So I highly recommend working through this section multiple times and using the print function in order to kind of really get a feel for how Google Earth Engine works, particularly if you're coming from a programming background that does not kind of use arrays as the default. So as I mentioned, in Google Earth Engine, an array is a list of lists, sometimes of lists. It's just lists all the way down. So a 0-dimensional array is a scalar number. A 1-dimensional array is a vector. A 2-dimensional array is a matrix. A 3-dimensional array is a cube. 4 and higher dimensions are hypercubes. So for any n-dimensional array, there are n axes numbered 0 through n-1. So for I'll say the thing that we use most often is probably a matrix or a cube, but we'll just stick to matrix. So for a 2-dimensional array, i.e. a matrix, there are 2 axes numbered 0 and 1. So 2 minus 1 is 1, so 0 and 1. So to illustrate this, the 0 axis is what we call the rows, and the 1 axis is what I would call columns. So these positions are really important to memorize. And then, if you're thinking about a cube, your 2 axis would be kind of like the stack of these. So if you have like an image cube, it would be those stacks. So highly recommend being really diligent about kind of working through these in your head and making sure they make sense to you. Yeah, so like I mentioned, Earth Engine uses the word axis to refer to rows and columns. So axis 0 and axis 1. And we can see how a list of lists is put together into a matrix. We'll use the tasseled cap example, but this is from a code perspective, right? Each time you open a square bracket, it starts a list. So it says start a list, and then the first entry of that list is a list. And then the second entry is another list, another list, another list, and then it closes it. So there's your list of lists and how you create it programmatically. One of the really great resources I found personally is a video by our co-author, Nicholas Clinton, and I've included the YouTube link for that here. It's a presentation he gave at Geo for Good, I believe, a couple of years ago. And it's literally an hour and 15 minutes of him talking about arrays. So understand that everything I'm kind of talking about is almost surface level, just to kind of get through a lot of this material. If you really want a deep dive, I highly recommend click on that link, watch that video. It's really an excellent resource. So briefly, some array manipulation functions and some of their uses. And again, there's lots. Feel free to use the user guide and just type in array, and it will populate with a whole bunch of these. But the most basic ones are image to array, which takes an image with multiple bands per pixel and creates an array image where each pixel is represented with a vector. This is also talked a lot more about in F4. So this is a little bit of a preview of array images, but array images are a pretty common tool used in some of the more advanced analysis approaches. So it's also used, the to array is also used to manipulate vectors into matrices. Then we have image.arrayProject. So this reduces the number of dimensions by keeping only the specific axes that are specified. The third is arrayFlatten. And this kind of undoes that previous function, right? So it turns an array image into a normal image with multiple bands per pixel. So the first example that we'll give is that we'll work through in the code is the tasseled cap transformation. This was really developed to distinguish different stages of wheat growth, but it's really useful for a number of different crops. A lot of grass crops do similar, like go through similar stages. And I created these little pictures of the matrices themselves for the text. Hopefully they help. I've included in the text both the like actual equation and like these pictures. I find the pictures helpful because it reminds me what the I'll say size of the matrix is supposed to be, how many rows and how many columns. So in this equation for the tasseled cap transformation, P0 is the vector of band values for the original pixel. R transpose is an array that's derived for each satellite. So this is not something, it's basically a constant. You can think of it as a constant. And if you use a different satellite, all you have to do is Google that satellite plus tasseled cap transformation, and there will be a paper that shows up that will provide RT for you. And so by multiplying these together, we get P1, which is the output vector for that specific pixel. So again, we're doing pixel-based transformations. So it's calculating one pixel at a time, and it will do that for the entire image. So the second example that we'll do will be to create PCA for an image and display the result. But I think what I'm going to do actually is run through the example of the tasseled cap transformation, and then we'll do the PCA. But since it's all one section, I'm just going to keep recording, and then we'll ask questions at the end. So I'm going to go ahead and run this F3.1 checkpoint, and then just turn off the pieces we don't need yet. Okay. So for our tasseled cap example, if we're thinking about that equation, we're thinking about the two pieces that we need to create the output, right? The first one is that our transform RT, we'll call it, and the second one is the list of bands convert for the image that we're interested in converted to an array image. So to create that first piece, we know that these are the values, right? We don't have to derive these. Someone has already done that for us. Thank you. The array is created with a list of lists, as we talked about. So opening bracket, and then our lists, and then our closing bracket. And then we've included a print function here, and I highly recommend using print as often as you need and or want to. It really helps me at least understand and make sure that the code that I've written is actually doing what I want it to. So we can inspect our Landsat 5 RT object, and we can see it's a list with 6 elements, and each one of those is in itself a list. So we then define the point of interest in, this is actually in Eastern Washington State. which is an area well known for growing wheat, which is why we chose it. Filter, display the true color image. So we can look at that true color image, and you can see each one of these circles is an irrigated wheat field. All right, so starting the tasseled cap, the creation of the array image. We first specify the bands that we're interested in. We then make the array image. And again, we use that toArray function, selecting the bands and converting them to an array image. Using these two pieces of code. So we then have that array image, and this is for each pixel, it's a 1-column matrix with 6 rows. And each one of those rows is the value from each of the bands. So this is how we get our P0. So now we do the matrix multiplication to multiply RT by P0, right? So we start with that matrix multiplication. So we start with the RT matrix, do a matrix multiplication with our array image that we've just created. And then here's how we start getting rid of those extra dimensions that we've created, because, and I'll say, this is just because of how Google Earth Engine works. So we then use array project of 0 to keep that 0 axis. And then we flatten the image. And using array flatten, you can specify the names of the bands you want to come out. So for the tassel cap, we know, and this is again, not something you need to know or that you should just intuitively know. This is something we know because this is a known transformation, and these are the things that each of these bands gets called, right? So it's always going to be this way for the tasseled cap transformation. And then we visualize this, and we're using the brightness, greenness, and wetness, and with minimums and maximums as specified. And those are, again, this is all say standard. So it's you can always change these maximum values, I'd say, but start with these kind of standard ones and you can tweak as needed. And then add this layer. So we can look at this. And so the brightness, greenness, and wetness have been mapped to our RGB. So wetness is going to come off very blue. Brightness will come off very red. Greenness will come off very red. Or sorry, very green. And so as you're going around, you can kind of look at these things. We can see our water is blue. The brightness one is red, but most importantly, we can start to tease apart the different stages of the wheat cycle that these are in. And so if you look at the RGB image and then look at the tassel cap transformation, you can start to see these kind of pop out, right? Where fields that are ready for harvest will appear one color, fields that are more bare soil will appear another, and then fields that are in various stages of growth appear in various shades of very bright. Not using brightness there as brightness, but rather using it there as there's a lot of light coming from my screen. So now let's dive into the PCA and how to create a PCA for an image and display the result. So this uses the covariance reducer on an array image. So we'll have to create an array image just like we did for the tasseled cap. and then it computes and extracts the eigenvectors. So this goes back to what I was mentioning before, where it does help to understand eigenvectors, but we're going to kind of gloss over that here. So we'll go through three kind of new, I'll say, functions here. Array get extracts an array from a function output. The array.eigen computes eigenvectors of an array, and the array slice extracts arrays. All right, so go ahead and pull our code window back. And go to our PCA example, turn off our tassel cap. All right, so here we're using Landsat 8. So we select and extract, select which bands to use, and then convert the Landsat image to a 2D array for the matrix computations. Now we use we're going to calculate the covariance of the matrix using the reduced region method. So reduced region is something we saw in F3.0 for running regressions. We're seeing it again here for the covariance. I will say, if you're wondering, anything that has to do with taking multiple things and kind of smashing them together, it's probably a reducer. So that's always a good place to look if you're wondering what function to use in Earth Engine. So here we start with that array image. We do reduce region. The reducer we're using is the covariance reducer. And then we provide a maximum number of map pixels just to make it so it doesn't get confused. So from that covar variable, we need to now extract the covariance matrix and store it as an array. So the covariance array variable will be, we're telling Earth Engine, store as an array this array we get from the covar variable. So this is the array that we're getting the array from. I also would encourage you to add more prints to this if while you're going through this code, because it is very helpful in terms of seeing what each of these steps does. So next, we compute and then extract the eigenvectors. So from this array that we have extracted, we do the eigen function to create the eigens variable, and then we slice out this 1,1 piece of the eigenvectors. We then perform the matrix multiplication of those eigenvectors multiplied by the array image sent to an array. And then finally, sorry, I'm going over this pretty quickly because each of these pieces is really complicated, and many of them will be addressed more deeply in future chapters. So I apologize. Again, highly recommend you read if PCA is unfamiliar to you, if you don't know the calculation steps, which is basically all this is doing, with some added complication from how Earth Engine treats matrices as two-dimensional arrays. And then use the print function and look at the two together, and you'll see that all it's doing is the PCA. So here's where we get into the flattening side. So we now have an array that has more dimensions than we need for each pixel. So we can throw out the unneeded dimension. We only want to keep those rows. Or yeah, I guess the better way for me to put this is what we're looking to extract from this is for each pixel, that one vector that has the useful data in it of each of the principal components. There's a whole bunch of other data that gets, there are unnecessary pieces of the Earth Engine creates more pieces than you need. So this simplifies it back down to that piece that you want and would expect from this output. So we then flatten this into each of our bands, and this flatten will make it as a normal image so that we can map this essentially. So in the text, so if you notice this piece of code here, it's just one of the things, and we have you map this in the text in order to illustrate how you can find appropriate minimums and maximums. So one of the things that you can do is, for example, use the inspector here, and it will give you, different values for that, and you can kind of start to see, oh, well, this is what I should use as my minimum, this is what I should use as my maximum. So you can do this for each band. You can also plot them. You can also, there's a couple of different approaches, but that's the one I believe that we use in the text. And this, with the values that we then kind of come up with, we can create a map of using the different principal components. So again, because this is a principal component analysis, the different principal components will have different, I'll say, meanings. So you may, and I will say this varies based on your location. So the satellite you're using, the location you're in, your thing of interest, your environmental piece of interest will kind of change how you do this, as it would with any other PCA, right? So when you're trying to visualize information by plotting it, how you interpret a PCA, there's not really a one size fits all. So how we've chosen to do it here makes it good for visualization here. But that doesn't necessarily mean that these particular components or these particular values are going to be applicable worldwide. They just happen to work well here, and we're showing you in the chapter how to kind of arrive at those. So I'll just preface it by saying this is an extremely broadly used approach. It's frequently used in conjunction with other approaches, but it's frequently used as, I'll say, a first step. The basic idea behind spectral unmixing is that in your image, a given pixel is likely comprised of multiple different things. So if you think about a single pixel that's in an agricultural field, for example, it might include signatures, spectral signatures from both bare soil and the plant that's growing. This is particularly important, I'll say, when you have pixels, for Landsat, right? You have a 30-meter pixel. If you think about, if you go outside and, measure out 30 meters and think about all the different things in the landscape that are in those 30 meters. So, you know, a 30 by 30 meter pixel is 900 square meters. So there's a lot of different things in 900 square meters. It can cause issues in downstream analysis with classification and regression, for example, because it's what's called a mixed pixel. So because there's pieces of multiple different things, sometimes the algorithm gets confused and doesn't quite know how to classify things, because it's like, well, you're telling me it's this, but this looks a lot like, you know, this. If you feed it mixed pixels, it will, you know, it just gets confused, right? Because the training data becomes it's using a mixed definition of that land use as opposed to a quote pure definition of that land use. So spectral unmixing models tease apart these different objects into quote pure spectra or end members. And we'll do a pretty, like what I just gave was a very, very quick overview. There's a very rich and diverse literature on this, highly recommended if you're interested in this approach, which is a very powerful one. So essentially, we have to solve for F. P is our band of pixels, and it's comprised of some pure end members multiplied by a matrix that essentially converts pure to mixed and vice versa. So we have to create this S. So unlike with the Tasla-Cap transformation, where this is already solved for, and it's the same kind of across an entire satellite, this differs based on your satellite and your location, and kind of what your what your end members are, I guess. So our steps are going to be first defining areas of the map representing pure objects. We then extract mean values for each band, combine these columns, and that creates S. And then we can solve for F using the matrix solve function. So let's go ahead and pull this back over. All right, so we're gonna use, so I won't be drawing the polygons. We'll do that. That's covered in the text, and it's also covered in previous sections in terms of how to do it in the Earth Engine interface. So I won't go into detail there in order to focus more, I'll say, on the arrayness of this chapter and of creating the transformations. So the first thing is, which bands do we want to use for the unmixing? Define those. And then we're going to use a false color composite to help define these. So we just map, we add that layer to the map, which is what we can see here. We then define polygons of bare soil, water, and vegetation. So this is a pretty simple example. I highly recommend you look into the literature if you want to do kind of, I'll say, more advanced ones. These can become pretty complicated. And so this is how, the fact that we specify these is for consistency, I'll say. in order to make it so that everyone has kind of the same basic ones. You can choose different ones and you'll see how your results change. So we then print a chart with these features, which I will pull up here. And this chart here, yeah, so we first specify the features and then we chart it. And I believe this was charts were covered more in F2 point something. I'm sorry, I forget which one it was. But in order to chart these, so this chart is really created for, I'll say, our knowledge, our understanding, and making sure this is a good check to make sure that our pure regions are actually pure. So we can, inspect this chart. It's the mean reflectance, and here we have each of our pure classes, and we can see how across the different wavelengths those change. And something that we would want to, so this is a good one because you can see that they are distinct across, as we look at the different wavelengths, the different bare water vegetation, pure, are very different across in terms of mean reflectance for those wavelengths. So something that we would want to avoid is to have these be kind of muddled, right? So they're sharing a lot of the same values at each of these wavelengths. So after this visual inspection to check, we can then get the mean for each region, at which point this is the region where the region is the image, right? So we start with our unmixed image, we reduce it using the mean reducer. So we use the image bands and we reduce it across the bare polygon, the water polygon, and the veg polygon that we've specified. Sorry, I want to make sure that's clear. And then we extract those values. We then stack these mean vectors for each of those polygons, for each of those bands in each of those polygons. And then we print that. So we have, oops, that printed down here. And so we can see that the list, so each row has 3 columns with different values, and those columns are the concatenation. We've squished those columns together. So each one is for bare, veg, and meat and water. So we then take this, we take our, so we've now come up with S. So now we have to create our P in order to solve for F. So let's create our P. We do this by converting our 6-band image into an image array. So 2 array, as we've done before, gives us our array image. And now we can solve for F. So here's where we use that matrix solve. We start with our, we start with our M members, and we matrix solve with the for the array image. Oops. And that will give us our F, which we've called unmixed. So we can then convert this back to a multi-band image using project and flatten and naming those bands. And then we add the unmixed. And as we've done RGB, so red is bare, green is vegetation, and blue is water. And this is where that image comes from. So you can see that all these pieces of water, the river, the reservoir, and some of these lakes and rivers over here show up as bright blue. The bare ground shows up as bright red. And the vegetation, which we can see all our crop circles or crop fields, circular crop fields, are showing up as bright green. Section 4 talks about the hue saturation value transform. This is, I would say, most frequently used to pan sharpen images. And this is a process by which a higher resolution, usually the panchromatic band, is used to augment the resolution of the red, green, blue RGB bands. This is actually so common that there are built-in functions for doing it. And we have a example that I've just stolen here from the book that I created, where on the left, it's the true color only, and then on the right, it's the pan sharpened image. So you can see how useful this is. It's particularly, well, it's useful for a whole bunch of things, but if you're doing things such as, creating some of the polygons for your end members, if you are defining fields or forest sections or something like that, that you are then going to use as training data for a regression or a classification, pan sharpening your image can really help with the human interpretation side of things. So instead of just doing instead of creating a polygon using the pan sharpened image can be a lot easier for human interpretation in order to create that training data, et cetera, et cetera. So that's one good use of it. All right. So the code for this is actually pretty simple. Again, like I said, there's two built-in functions. One to convert RGB to hue saturation value, and the other one to go backwards from hue saturation value to RGB. So let's pull up that code. All right, here's our transformation example. You can see it's very short. So for this example, let me we'll start with our false color. All right. So for this one, we're gonna select our red, green, blue bands from our Landsat 8 image. And we're just gonna take those and feed them into the RGB to HSV transform. And all that does when we map our HSV transform is take the RGB values and extract from each pixel its hue, its saturation, and its value. Oh, it occurs to me, I probably should have put a slide in here in it to talk about what each of those is, but that's done in the text. So basically, hue, color, saturation, how much of that color, I forget what value stands for. I think it's brightness. Anyway, Jeff, please correct me when I'm wrong about that one. But now that we have that hue, saturation, and value, we just use a sneaky little trick. We keep the hue and saturation, and for the value, we use the pan sharpened, the panchromatic band for the value. And panchromatic is usually if you just map it, it's from black to white. And it is generally detected by satellites at a higher resolution than the red, green, blue. So if your satellite, such as Landsat does, has a panchromatic band at a finer resolution, so this is a 15-meter resolution. Each pixel is 15 by 15 meters instead of a 30-meter resolution, 30 by 30. So basically there are 4 pixels in the panchromatic band for every 1 red, green, blue pixel for Landsat 8. And because it is a panchromatic band, i.e. black to white or white to black, we can substitute that for the value. So we can simply concatenate those 3 bands, which I will point out, Earth Engine is great because it lets you pull bands from different pieces, as we did for our regressions. And then we just feed the concatenation into the built-in function to convert HSV to RGB. And what comes out of that is our pan-sharpened image. So if we compare just quickly our pan-sharpened image to our false color image, you can immediately see how much easier that is to visually interpret. You can see much more clearly where the defined edges of the fields are. So this one's a nice, easy one to end on, and it is a fantastic tool to use for all sorts of things as a pre-processing step for your analysis.